Good morning. We've almost made it. So normally on the day before the AP test, we kind of relax a little bit in class. We would have our typical 48 minutes together, and then I shoo you out the door and wish you good luck. So we'll kind of maybe do the same thing today. I mean, usually we would go over the equation packet and take any last minute questions. I mean, now I guess you got the whole day to study or whatever you want to do. So that part's nice. Now, hopefully you have your equation packet. Thankfully, I had one like shoved in my backpack. If you don't, you might want to find a way to print one. I mean, obviously, you could have it open on a tab on your computer. That's totally fine. But I think it's going to be easier if you have it handy and you could write on it if you need to. So some things that you might want to have written on it. If you don't already, I would maybe mark in the orbitals and the energy levels so that it's a little quicker, easier to do electron configurations. So I would mark in the S block is the first two groups across, the P block being these last 6 groups across, the D block in the middle, and then the F block at the bottom. But I highly doubt they're going to ask anything about F orbitals. Then I would number my energy levels. The S orbitals are found in every energy level, 1 through 7. The P orbitals don't start till the 2nd energy level. And the Ds don't start till the 3rd. That might be the most important thing, is to mark in the 3D. We fill orbitals lowest overall energy to highest overall energy. And it just so happens that the 4s, even though it's a little bigger orbital by like radius in the 4th energy level, it's a little further from the nucleus. But with it being an s orbital, it's a low energy orbital. And overall, if we take all factors into consideration, the s orbital in the 4th energy level does have less energy than the 3D orbitals. And even though they're a little bit smaller by radius, they're high energy orbitals, and there are 5 of them. So when we fill lowest overall energy to highest, if you mark this in, you'll never get it wrong. That we'd fill 4s2, 3d10, and then 4p6, and so on. You could also do like a noble gas shortcut as well. With that too, I would remember that if they ask you for an electron configuration of an ion, you have to take the charge into consideration. So if they ask me for like a magnesium ion, a magnesium +2 ion would lose 2 electrons. And so then I would really be down to 10. And I would do the noble gas electron configuration of neon. Now you could write neon in brackets or just write, I mean, neon's not crazy long. 1s2, 2s2, 2p6, done. What else should I mention about electron configurations? Yeah, that might be pretty good for configurations. Other things that we might want to remember about our periodic table, maybe charges. I would make sure I have marked in +1, +2. Skip the transition metals. This is where you'll see a Roman numeral, and the Roman numeral will indicate the charge because often more than one charge is an option for transition metals. +3. Technically, we could say plus or -4 for the carbon family. But in all honesty, usually the carbon family goes covalent and shares electrons. Maybe not so much like when you get down to tin and lead. They're metals and they'll transfer. But carbon, silicon, germanium will usually share. But that's the turning point. Then -3, -2, -1, 0. Now these would be the charges if I'm making an ionic compound, but they may not be the same as the oxidation number. So for example, like if I had the compound NO2, whoop, there it is, nitrogen dioxide, and I were assigning oxidation numbers. Well, oxidation numbers are a little bit funky when you get to something covalent. We just try to show not that electrons are transferred, but if they're shared, where are they being drawn closer to, the nitrogen or the oxygen? And then we'd say, oh, with nitrogen, or I should say oxygen, having the higher electronegativity, we're going to give the oxygen a -2. The electrons will be drawn toward the oxygen. There would be a total of 4 electrons pulled toward the oxygen, which then would give the nitrogen an oxidation number of +4. Don't freak out, because that's not what I put on my periodic table. Because these charges are for ionic compounds. These are oxidation numbers, and they are little charges. But when it's a covalent particle, it might not match to these that we listed for ionics. I also have to remember that if I'm doing oxidation numbers for an ion, like a polyatomic ion, then let's say I had MnO2 permanganate, the -2 permanganate ion, I do have to take into consideration the overall charge on the ion. So the oxygen would still be a -2. There are 4 of them. That gives me a -8. Oopsies, I want this to be I'm going to use the -1 version. I think that's the one that we use more often. If I use the -1 version, then my manganese should be a +7. I think that's the more common one that we've seen. And the one that we used in the lab was this -1 version. Sweet. So make sure you take into consideration the charge if you're doing oxidation numbers for a polyatomic ion. Okay, so there's a little atomic structure that I can get off the periodic table. When it comes to trends, periodic trends, they're not just going to ask you like, which element has a higher radius, this or that. They might just tell you, hey, the radius of sodium is larger than lithium. Explain why. And they might want me to explain in reference to Coulomb's law. Coulomb's law is this relationship that helps us to gauge the degree of attraction between oppositely charged objects. We can use that with atomic structure, where Q1 and Q2 would be the charge on the electron cloud and the charge on the nucleus. So the number of protons versus the number of electrons. And then R is the distance between them. So if I were explaining a trend going down, and maybe it was like between lithium and sodium, explain why the radius of sodium is larger. Other trends going down a group, maybe they might say, explain why the ionization energy of sodium is less than that of lithium. We'd say, okay, I got this. So Q1 and Q2 are the charges, which obviously they are going to have a different number of protons and a different number of electrons. But more importantly, going down a group, a lot of the trends are dominated by R. The fact that each time we go down the group, we're adding electrons to a higher energy level. And so that R value is larger. And Coulomb's law is kind of a general term for this relationship. But when we talked about it in terms of attraction between oppositely charged particles, this might be ionization energy. If we're thinking about atomic structure, if they said, why is the radius larger in sodium? Oh, because we're in a higher energy level. Why is the ionization energy of sodium less than that of lithium? And then we'd say, oh, okay, if they're telling me it's less, then it's got to be the fact that this radius is larger. Yeah, I mean, the charges are also different in sodium versus lithium. But if they tell me that the radius is larger, then, if they tell me that the ionization energy is less, I should say, then I'm going to explain it in terms of R, the radius being larger, and that's going to make my ionization energy less. You could also explain it in terms of just the degree of attraction, that if the electrons are farther from the nucleus, then the attraction is weaker and it takes less energy to remove those electrons. Going across, I'm just filling an energy level. So if I'm going across the second energy level, in general, all of these electrons being added are added to the same energy level. So they're on average the same distance from the nucleus. R is kind of the same going across. Then that's when I go to Q1 and Q2. So if I'm explaining a trend in maybe electronegativity, going across from boron to fluorine. Well, yeah, I mean, overall, R is pretty similar, but as I go across, I'm going to have 9 protons and 9 electrons in fluorine versus 5 protons and 5 electrons in boron. Greater charges, greater attraction. That's going to also increase the attraction for electrons in other atoms. It's going to make the radius decrease going across if there's a stronger attractive force. Somebody asked about electron affinity energy. It's the energy released when I gain an electron. It's, for the most part, directly related to electronegativity, that if fluorine has a higher electronegativity than oxygen or nitrogen or carbon, well, then it's more likely to gain electrons. And when I gain electrons to fill the outer shell, then it's more likely to release more energy as well. Awesome. One other thing that maybe we should mention too, in terms of periodic trends and radius and all that stuff, ionization energy, be careful of those isoelectrics. So isoelectric might be something like the fluorine -1 ion versus, let's say, the sodium +1 ion, where they're going to simplify the same number of electrons. They're all going to simplify to 10 electrons. So now if they ask me trends about like radius or ionization energy, now I have to look at the number of protons in the nucleus, where this guy is going to have 10 electrons, but still only 9 protons. The sodium ion is going to have 10 electrons, but we'll still have 11 positive protons. So if they ask me about like radius, okay, well, here they're both going to simplify to the same number of protons, or hello, electrons, but with sodium having an extra proton, stronger attraction. Q1, Q2, this is going to be stronger up on the top. That extra proton is going to make for a stronger attraction, smaller radius. Or I might say stronger attraction, greater ionization energy. If I wanted to remove another electron, it's going to take more energy to remove the electron here. Be careful too if they ask you to like identify an element and they talk about successive ionization energies, that, you know, we see this big gap in ionization energies when I jump from valence electrons to core. So like in either of these, I don't want to lose any more electrons because that would be removing the stable electrons in the core. But if they did give me like that list of successive ionization energies, once you see that big jump, that's the switch from valence to core. And sometimes then they might say, you know, this is an element in the 3rd energy level. And I could tell by that chart, ooh, the big gap is from like maybe electron 2 to electron 3. So I don't mind losing 2 electrons, but I don't want to lose the 3rd. And so then maybe we'd say, okay, well, yeah, that would be something like magnesium, where magnesium would lose 2 electrons, and then I'm down to my stable configuration with full orbitals, but I don't want to lose the 3rd. And something like aluminum would be happy to lose a 3rd electron in the 3rd energy level, but not magnesium. Switch from valence to core. That tells me like how many valence electrons. And if they say that, yeah, it's in the 3rd energy level, then that would help me to identify the element going across. Awesome. Now, if we switch gears a little bit, we could also think of Coulomb's law as lattice energy. And lattice energy would then be for ionic compounds, where they might say something like sodium chloride versus calcium chloride. And they might say, like, you know, what compound is going to require more energy to separate the ions? This might come into play if I'm talking about solubility. The first step in dissolving an ionic compound in water is an endothermic step where I have to add energy to separate these ions. Now here I'd say, okay, I got a +1, I got a whoopsies, -1. Here's a +2, -1. First thing I look at is the charge, the magnitude of the charge. If this guy's got higher charges, this one's going to have a higher lattice energy, and it'll take more energy to separate the ions. Now, if they give me something where the charges are the same, then I'm going to look at R, the radius. So maybe I have like sodium chloride versus, oh, I don't know, rubidium chloride. And they're both +1, -1, +1, -1. So the charges are the same. Then I look to the radius. And we'd say, okay, whichever one has a smaller radius, I'm dividing by a smaller R value, that's going to make the attraction stronger. The ions are smaller, they're closer to each other, and then it's going to take more energy to separate. And so that then would be these guys. The sodium ion would be noticeably smaller than rubidium. So if I'm dividing by a smaller R, lattice energy is higher, meaning the attraction is higher. It's going to take more energy to separate the ions. Good stuff. Now, you might have even more on your periodic table from throughout the year, and that is fantastic. You can have any notes you want on here. So you can go through like the Chapter 7 study guide. You can write whatever you want if it helps you, but make sure that it's obviously legible and not super crazy so you can't find anything. Okay, then going to the inside. A couple reminders on the inside here. Number one, we've got two equations in the atomic structure section. This second one, speed of light equals frequency times wavelength. The speed of light is in meters, which means that your wavelength needs to be in meters. So I might put that in there. I want this in meters. If they give you nanometers, we're going to have to switch that. And so then we might say that there are 10 to the 9th nanometers in 1 meter. And I could use that as a proportion. Nanometers are super crazy tiny fractions of a meter. Frequency would be like waves per second, cycles per second. It's probably units of like 1/seconds. And so that might be the only thing I have to be a little bit careful of with this second equation. Now, it's possible that maybe you're given enough information to use this second equation and solve for wavelength. And then maybe I plug that into the first equation and solve for energy. How much energy is required to remove an electron, or how much energy is released when this electron moves from energy level to energy level. And then E would be Planck's constant, which involves joules. And then I would use my wavelength. Now, if they gave you that in reverse, or maybe they gave you the energy value, and I'm going to solve for wavelength and then plug my frequency. Maybe I'm going to solve for frequency and plug that into the second equation and solve for wavelength. Or they might say, you know, like what wavelength of light is produced, or what color of light, and then I match it up to different wavelengths. Then just be careful that if they're giving you an energy value, it's got to be in joules in order to use Planck's constant. So often these two equations are used hand in hand. Then the other little equation, or the other little constant they give me here, the charge on an electron. I don't know the last time I saw that on the AP test. This goes back to this Millikan oil drop experiment. I mean, really, the last time I saw it, I think it was in a multiple choice question where electrons come in charges of this amount, this magnitude. And so if I had an oil drop that had a charge of like negative 3.2 times 10 to the negative 9th coulombs, then we could say that oil drop had accumulated 2 electrons. I highly doubt this will be on the free response questions this year. I mean, there's way more important things they should ask you about than this thing. When you get to the equilibrium section, some good news. The only things that we're going to focus on are these guys. All the rest of this is acid-base, and they're not going to ask about it this year. So the only thing here that is going to help me is just knowing how to set up an equilibrium expression. It could be in terms of concentrations or pressures. But again, somebody had asked about like the brackets and the parentheses. It's fine if you interchange them. They're not going to not award you the point because you used parentheses and it was traditionally shown as brackets when I use concentration. Not something to worry about. But the rest of this, good news. This is all for acids and bases, buffers, titration curves, not on the test. Woohoo! And then finally, when I get down to kinetics, you might want to mark in that these are the integrated equations. This is my zero order. So if I have a graph of just concentration versus time, if it's linear, that's going to be a zero order reaction. If I have a linear graph where they're using natural log over time, that's my first order. I suppose I could put zero order. And if my linear graph has 1 over the concentration, that's my second order. Now, these equations are used when you want to do a calculation that involves time. So maybe off the graph, I could identify it as a first order reaction. The natural log versus time was linear. And now they, in a further question, asked me to calculate something involving time. And so it might be like, how much time will it take for the initial concentration to decrease to this given final concentration? I might be solving for time. Now, K, I could get off the graph. The equilibrium the kinetics rate constants are related to the slope. Now, we want them to be positive. K is always a positive. When you're looking at kinetics rate constants. So if you would have a negative slope, then you would just take the absolute value, which would be the case like with these guys. You're going to end up with a negative slope. Take the absolute value if they're asking you to like determine the value of K. If then I knew the value of K, I got the slope of the line or something like that, then I could plug in K, I could plug in the initial concentration and maybe the given, and I could solve for time. Or maybe they say after so much time, what would be the final concentration? Right, plug in time, I've got K, probably off a graph, I got the slope. They give me the initial concentration, and then I want to solve for the final. And you could do that same thing with any of these equations. We would just need to know the order of the reaction. And then finally, they give you half-life. Half-life, we could mention, is a first-order reaction. So you got a couple ways to solve for half-life. If they give you a graph and you know that it's first order, you could just estimate off the graph. You'd want the graph of concentration versus time. And usually it would look like this if it was just concentration versus time. And maybe then they also gave me one that was like natural log versus time. And then I could say, oh, the natural log graph is linear. It's first order. You could estimate the half-life just looking at how much time does it take for the concentration to go down by half. Or if you knew K, like if you found the slope of the linear line, the linear fit graph, the natural log graph. If you knew K, you could plug it into this little equation. This will let you solve for half-life. Or probably too much work, you could use this guy too and just solve for the time it takes for the initial concentration to go down by half. But this one's probably the best option. It's the quickest. You would just need to know K, which maybe you could find the slope of the linear graph. All right, there's some good kinetics. Then on the back side, we've got gases, liquids, and solutions. We have our perv-nert. With perv-nert, we just want to watch the gas constants. So maybe we would mention that these guys are for perv-nert. These are your options for R. Just make sure that you use the right pressure unit if they're asking for a particular pressure unit, or if they don't specify that we want the pressure in atmospheres, make sure then you put a pressure unit behind your final answer if you're solving for pressure. This is kind of a funny equation. It's for mole fraction. This thing here is called mole fraction. And we use this with partial pressure of a gas, where maybe I had like the total pressure of a gas, the total pressure was 10 atmospheres on a mixture of gases. And I knew that one particular gas was 20% of the mixture. I could say the total pressure was 10. The mole fraction of a particular gas, gas A, maybe that was like 20% or 0.2, which then if 20% of the particles are gas A, 20% of the collisions are gas A, 20% of the pressure is gas A. And so then we'd say, okay, the partial pressure, this is the partial pressure. The partial pressure of gas A would be like 2 atmospheres. The pressure coming just from one particular gas. This one always makes me chuckle too. Good Lord, like we really need this in the packet? That the total pressure on a mixture of gases is just the sum of each individual pressure. Here they tell you how to calculate moles, which is crazy. Like moles would be mass over molar mass. I might also kind of mention that molar mass then is grams per mole. And this is a common calculation that you might do either with titration data, or maybe somebody like calculated the mass of a precipitate and I want to try to identify the compound. If you knew the mass of the sample and you knew the amount of moles in your sample, you can calculate molar mass, and that's a good way of identifying an unknown. They give me the switch from Celsius to Kelvin. They give me density. This guy here for kinetic energy, I haven't seen used in a way that you have to calculate kinetic energy or velocity or mass. But this one does help me kind of maybe compare the speed or the rate of moving gas particles as a function of their mass. And so mass and velocity, this little v is velocity here. Mass and velocity are inversely proportional. That if I have a higher mass, the particle is going to move at a slower speed or a slower velocity. But kinetic energy is related to temperature. And so like I might have the same temperature, particles at the same temperature, where there's the same amount of energy being applied to the particles, but then the higher the mass, the lower the velocity. Or the lower the mass, the higher the velocity. They give me molarity, moles per liter. And then finally, this guy. This is that Beer's law. This is the one that we did in the lab with absorbance of light, where A, big A, is the absorbance of light, which they'll probably give you either on a graph, or maybe they tell you that, you know, my purple colored solution was put into a spectrophotometer or a colorimeter where a certain wavelength of light was shined through the solution. Depending on the concentration of the solution, a higher concentration will absorb more light and a lower concentration will absorb less light. So A would be my absorbance. This little guy is a constant, the molar absorptivity constant. B is your path length. That's like the width of the cuvette. Like our cuvettes are about 1 centimeter. So that's probably measured in centimeters, millimeters. And then C is the concentration. These are the most important parts of this equation. That absorbance and concentration are indirectly proportional. I mean, directly proportional. Good Lord, it's super early in the morning. That the higher the concentration, the higher the absorbance of light. And so often we would be solving for one of these two. And these guys are, for the most part, constant. Cool. There's my gases, liquids, solutions. I mean, if you wanted, you could put Coulomb's law in somewhere, or maybe you'll have it written on the front side. That's usually one that I kind of wish was given. Another one that sometimes I kind of wish was given was that M1V1 equals M2V2. This guy's for dilutions. Maybe they give me a solution and I have to describe a procedure for diluting the solution. Remember to do as you oughta. Put the acid in the water. Put that in here. Acid goes in the water if I'm diluting an acid. And it's just because it's exothermic and a little energy is released, and we don't want that energy released to vaporize or evaporate any of the water. We want our volume to be accurate. And then finally, some questions were asked about the thermo and electro, where people were like, can you review delta G? Or somebody had said, oh my gosh, I was looking at some free response from past years, or I've got like a Princeton review or whatever, and they start talking about cell potential and some of this cool stuff, but it's not on the test. So actually, there's only 2 equations in this section that are still fair game. This guy, Q would be my heat, equals MC delta T, mass times specific heat times temperature change. That guy is still fair game. And this one is still fair game. But they're not going to ask specifically about entropy or delta G. None of these guys. And the rest of them are electrochemistry, which also is not covered on this year's test. Well, that makes it a little better, so you don't have to worry about delta G. This guy is used to calculate the energy change for a chemical reaction if I'm given data that's heat of formation. And so then I go total heat of formation of my products minus total heat of formation of my reactants. Now, the other one that we might want to add would be that delta H can also be calculated using bond energies, where it would be total energy of the bonds broken minus total energy of the bonds formed. And here's where they're going to give you data that's like specific to the types of bonds involved in the reaction. The carbon-carbon single bond, the carbon-carbon double bond, the carbon-carbon triple bond, or whatever it might be. And it might be helpful to either draw out the Lewis dot structures or kind of think about what types of bonds would be present. Are they single bonds, double bonds, triple bonds? And then to also think about how many bonds are in that particle. So like if I had carbon dioxide, I would want to know that it's 2 double bonds. If in the balanced equation I had like 2 moles of carbon dioxide, then I would say, well, I've got to break 4 moles of these carbon-oxygen double bonds. Cool. That also just made me think, like, not that this is really on the packet, but it also kind of made me think of these graphs, like those energy graphs that are like maybe something like that, where the bond is formed at the lowest energy level. And this is usually some kind of energy, maybe kilojoules. And this is internuclear distance, where the bond is formed at the lowest, most stable energy level. And so like this might give me the bond energy. And then if I follow it up, this would be like the internuclear distance, the distance where I can maximize attraction and minimize repulsion. But I could also kind of use this graph in reference to like single bonds, double bonds, triple bonds, where if I had a double bond, I might have a shorter, okay, let's see if I can do this, a double bond or a triple bond, a shorter internuclear distance, but maybe I'd be releasing more energy. Whoa, that's not too bad. Something like this, like maybe this is a, I don't know, maybe it's like carbon-carbon single bond. This could maybe be like a carbon-carbon triple bond, where it would be a shorter bond length, but it would take more energy to break that bond. More energy released when it formed, but more energy required to break the bond. That just totally popped in my head. And so a lot of these you won't use, like you won't need this, you won't need this, you won't need these guys, current, You won't use G, you won't use S. Oh my gosh. Oh my gosh, Q, the reaction quotient. This maybe just sparked my memory too. When you do equilibrium, Q looks just like K. Q calculations looks like K. The only difference is that Q, but we use initial pressures or concentrations, conditions, I'll say. And they might not represent equilibrium. And so that's usually what we're trying to figure out. With the conditions given, am I at equilibrium? And if not, in what direction am I trying to shift? But that's where we can say if Q is equal to K, we are at equilibrium. If Q is greater than K, I want to look at this expression. It's products over reactants. So if Q is too big, I have too much product. Here's my product. Well, I want to reduce Q so that it equals K. We want to be at a state of equilibrium. If I have too much product, I'm shifting this thing in reverse. If Q is less than K, then I don't have enough product. I want to make more. We would shift forward. Now, in reference to solubility, somebody asked a question about solubility too. We can use Q to predict whether or not a precipitate forms. So in reference to solubility, if Q is bigger than K, and Q are the products, in solubility, the products are the ions. So maybe I had something like, silver chloride forming silver ions and chlorine ions. Well, now if Q is too big, we've got too many ions in the solution, and in order to reduce the number of ions, I'm going to form a precipitate. If they're asking about like KSPs and some of that stuff. If Q is too small, well, then we don't have enough ion for a precipitate. We'd say no precipitate. And in fact, we would probably be forming more ion in order to get Q to a point where it equals K. Awesome. So here might be a little walk through the equation packet, some of the most important parts of the packet. I'll also post the video then of all the questions that were specifically asked in Canvas too. Some of them were covered in here, and there are a couple other really good ones that I will also post for you in Canvas. All right, here we go. We can do this.